not gonna work.
Why didn't you say so before?
I did say so before.
Greetings, cadets. There are many ways to create a landing strip or runway effect for a shuttle bay. The correct name for this effect is an LED chaser circuit. This is the first of two segments where we will look at different chaser circuits, each with its own particular advantages and disadvantages. In this first segment, we will examine two circuits which can be prototyped using an ATtiny to control the chaser effect. The first circuit will feature an ATtiny hooked up to a decade counter, while the second circuit will feature an ATtiny in conjunction with a shift register. By looking at all the options, we can decide which one would best suit the project we're working on. So, without any further ado, let's get cracking. Before we delve into the actual circuit building, we need to have a closer look at a particular microchip, the 4017 decade counter. In the same way that we use the word decade to mean 10 years, the decade counter is an integrated circuit chip which can switch between 10 outputs, one at a time. When a clock pulse is applied to it externally, its outputs become logic high and low sequentially, one at a time. So, looking at the chip with its notch at the top, it means that leg 1 will be at the top leftmost corner. As always, we number the legs in a counterclockwise direction, starting with leg 1 downwards to leg 8 on the left-hand side. Moving to the right, we number leg 9 upwards to leg 16. Leg 16 gets connected to the positive power of the circuit, and it operates in the range of 3 to 15 volts. Leg 8 needs to be connected to the ground part of the circuit. Leg 15 is the reset pin and is normally grounded, which means it isn't active. When this pin gets triggered or set to high, the decade counter resets its outputs and starts counting from LED number 1 again. This is handy if we want to limit the output to fewer than 10 LEDs. For example, if we need only 6 LEDs, we can connect output 7 of the decade counter to this reset pin to restart the sequence. Likewise, we can control it externally by connecting an Arduino output pin to this leg. Leg 14 is the clock pin, which is the driving force of the 4017 chip. Each time it gets switched from a low state to a high state, it advances the output to the next LED in the sequence. The speed at which the 4017 works is directly affected by the clock frequency. The faster the impulses get sent to the clock pin, the faster the LEDs will light up in sequence. Leg 13 is the enable clock pin. While this pin is held low, the 4017 works normally. If it is set high, then all operation stops. For this reason, we connect this leg to the ground part of the circuit. Leg 12 is the carry-out pin. It's an interesting pin because after the last LED lights up, this pin becomes active and allows us to piggyback another 4017 chip which can be activated if we want a sequence of more than 10 LEDs. Once leg 12 switches on, it remains active from the first to the 5th LED in the sequence. Now here's where things start to get a bit freaky. The outputs seem to have been numbered by someone with a strange sense of humor, or a love of Romulan ale.
Worf? Are you alright?
Romulan ale should be illegal.
It is.
Leg 3 of the 4017 chip connects to the first LED, leg 2 to the second LED, and leg 4 to the third LED. So far, so good. Now, leg 7 connects to the fourth LED, and, believe it or not, leg 10 connects to the fifth LED. Moving back again, Leg 1 connects to the 6th LED, leg 5 to the 7th LED, and leg 6 to the 8th LED. Now, where were we? Oh yes. Leg 9 connects to the 9th LED, and leg 11 connects to the 10th LED. That's quite an interesting arrangement. Once wired up correctly, however, the 4017 is a very capable little IC. In our first circuit, we will connect an AT-Tiny to a 4017 decade counter. To do this, we need the following components: a breadboard, an Arduino Uno, and some jumper wires. We also need an AT-Tiny 85 chip, a 4017 decade counter, 2 by 10 kilo ohm pull-down resistors, one 47 kilo ohm resistor, a momentary button switch, 10 1 kilo ohm resistors, and 10 3mm LEDs. The disadvantages of this circuit are that the shuttle-based sketch first needs to be uploaded to the AT-Tiny, and also that the AT-Tiny can only operate at voltages between 3 and 5 volts, so it needs to either feed off the 80 megas power supply, or it needs its own dedicated power supply. Another disadvantage is that it has more parts than the second circuit we'll be looking at, which means more work soldering it up and more components which could fail over time. There are some advantages to this circuit, however. It has a built-in response to the red alert signal from the 80 megachip, and the number of lights as well as the speed of the chaser sequence can be controlled via software. Also, the decade counter can handle up to 10 lights on its own. Before we can build our circuit, we need to program an AT-Tiny 85 chip with a shuttle-based sketch. Our first step is to connect the Arduino Uno to our consoles and open up the Arduino user's interface. We click on Tools and make sure that our board parameters are set to Arduino Uno and that the correct COM port has been selected. Then we click on File, navigate down to Examples, and open the Arduino ISP sketch. A new window opens with the Arduino ISP sketch, and we click the Upload button on the user interface. First the sketch compiles, and then it uploads to the Arduino Uno and turns it into an in-system programmer. Once it's done uploading the sketch, the Arduino Uno can be used as a programmer for our AT-Tiny 85. The next step is to download the Shuttle-Bay DC as in decade counter sketch. The link is in the description below. We copy this link and paste it into our browser's address bar. We select the download button and save the sketch to our Arduino working directory. Once it has downloaded, we select the file and run it. We click OK for it to create a folder, after which it opens in our user interface. Once again we navigate up to Tools and change the board to AT-Tiny. We select AT-Tiny 85 as the processor, change the clock to internal 8 MHz and the programmer to Arduino as ISP. We wire up the AT-Tiny for programming, as discussed in a previous segment. Navigate to the bottom of the Tools menu and select Burn Bootloader. To upload the sketch to our AT-Tiny, we let the cursor hover over the Upload button, then press the Shift key to change the dialog to Upload using Programmer and click the Upload arrow. The TX and RX lights on the Arduino Uno flicker briefly as the sketch is transferred to the AT-Tiny. Once the AT-Tiny has been programmed, we can start to prototype our circuit. We connect the upper rail of our breadboard to the positive wire of a 5-volt power supply and the ground rail to the negative wire of our power supply. We bridge the lower ground rail with the upper ground rail using a jumper wire. We add the programmed AT-Tiny in such a way that it straddles the gutter of the breadboard and its notch faces towards the left. We connect leg 4 of the AT-Tiny to the lower ground rail using a jumper wire. Leg 8 of the AT-Tiny gets connected to the upper positive rail of the breadboard using a jumper wire. We connect leg 2, which is our red alert input pin, to the ground rail using a 10 kilo ohm pull-down resistor. Next, we add our decade counter to the breadboard so that it too straddles the gutter and its notch faces towards the left. We connect leg 8 of the decade counter to the ground rail using a jumper wire, and leg 16 to the upper positive rail of the breadboard. Leg 15, which is the reset pin, gets connected to the ground rail via a 47 kilo ohm pull-down resistor. We connect leg 13 to the ground rail using a 10 kilo ohm resistor. We connect leg 5 of the AT-Tiny to leg 14 of the decade counter. This is the clock pin, which determines the speed of the chaser sequence from one light to the next. We connect leg 6 of the AT-Tiny to reset leg 15 of the decade counter using a jumper wire. Now, moving further across, we connect 10 rows of the breadboard to the upper ground rail using 1 kilo ohm resistors. We connect 10 LEDs in such a way that the negative legs are connected to the same row as the resistors, while their positive legs are inserted into empty rows on the opposite side of the gutter. We connect leg 3 of the decade counter to the positive leg of the first LED using a jumper wire. In the same way, we connect leg 2 of the decade counter to the second LED and leg 4 to the third LED. We connect leg 7 to the fourth LED, leg 10 to the fifth LED, leg 1 to the sixth LED, leg 5 to the seventh LED, and leg 6 to the eighth LED. Finally, we connect leg 9 of the decade counter to LED number 9 and leg 11 to LED number 10. In order to simulate a red alert input signal from the 80 mega chip which is running the main circuit, we'll add a momentary button to the chaser circuit. We connect one of the legs of the button to the positive rail using a jumper wire and connect the diagonally opposite leg to the input pin of the AT-Tiny, which in this case is leg number 2. If we do not plan to use the red alert effect in our Starship, we can ignore this connection, but we still need to include the 10K pull-down resistor on leg 2 of the AT-Tiny. Once we power up the circuit, we notice that the chaser sequence progresses steadily along. As soon as we press the button to send a red alert signal, the sequence speeds up and the lights move twice as fast until we let go of the switch and everything returns back to normal again. The number of lights in the chaser sequence and the delay between successive LEDs can be modified by changing values in the sketch. Both this first circuit and the second one can be customized by changing the values of two variables at the beginning of the sketch before uploading to the AT-Tiny. For example, we can downscale the number of lights to 6 by modifying this first value, and can make the sequence run faster by changing the delay between lights from 120 to 90 milliseconds. We can reset the number of lights back to 10, but this time we can make the sequence run even slower by using a larger delay between lights, for example 200 milliseconds. In our second circuit, we'll connect an AT-Tiny 85 chip to a shift register. To build this circuit, we need the following components: a breadboard, an Arduino Uno, and some jumper wires. Additionally, we also need an AT-Tiny 85 IC, a 74HC595 shift register, a 10 kilo ohm pull-down resistor, and a momentary button switch. For the chaser sequence itself, we need 8 1 kilo ohm resistors and 8 3mm LEDs. The disadvantages of this circuit are similar to those of the first circuit, as the shuttle-based sketch first needs to be uploaded to the ATtiny, and the voltage of the circuit is restricted to the 3 to 5 volts at which the ATtiny can operate. Also, we are restricted to 8 lights for our effect, which is all that the shift register can handle. It is, however, fairly easy to piggyback shift registers for a longer chaser sequence. This circuit does have some unique advantages over the other two. Firstly, it uses a minimum of components, which gives it a smaller footprint on the perf board, and there are less parts which could fail over time. Because we're using an ATtiny, we have a built-in response to the red alert signal from the ATmega chip, and the number of lights as well as the speed of the chaser sequence can be controlled directly via software. In fact, by using the shift register, we can make the lights do almost anything: switch direction, form simple patterns, and speed up or slow down at will. As in the previous circuit, we need to program the ATtiny85 to run the sketch which controls the chaser sequence. After we have turned the Arduino Uno into an AVR in-system programmer, we need to download the Shuttle Bay SR as in shift register sketch. To do this, we copy the link in the description below and paste it into our browser's address bar. We select the download button and save the sketch to our Arduino working directory. After it has downloaded, we select the file to run it. We click OK when the user interface asks to create a new folder and wait for the sketch to open. We click on Tools and change the board settings to ATtiny, the processor type to ATtiny85, and our clock speed to the internal 8 MHz setting. We make sure that the port setting is the one the Arduino Uno is connected to, and select the programmer to be Arduino as ISP. Once everything is in place, we select Burn Bootloader from the Tools menu to install a bootloader onto the ATtiny85. Finally, we hover the cursor over the Upload button, press the Shift key and click the Upload arrow. This burns the Shuttle Bay shift register sketch onto the ATtiny chip. Once completed, the user interface displays the message, Done uploading. After the process of programming the ATtiny has completed, we can add it to a circuit. We connect the upper rail of our breadboard to the positive output of a 5-volt power supply and the ground rail to the negative input of our power supply. We bridge the lower ground rail with the upper ground rail using a jumper wire. We add the programmed ATtiny so that it straddles the gutter of the breadboard and make sure that its notch faces towards the left. We connect leg 4 of the ATtiny to the lower ground rail using a jumper wire. Leg 8 of the ATtiny gets connected to the upper positive rail of the breadboard using a jumper wire. We connect leg 2, which is our red alert input pin, to the ground rail using a 10 kilo ohm pull-down resistor. Next, we add our shift register to the breadboard so that it too straddles the gutter and its notch faces towards the left. We connect leg 8 of the shift register to the lower ground rail using a jumper wire. Leg 13 of the shift register gets connected to the upper ground rail. Leg 16 gets connected to the positive rail, as does leg 10 of the shift register. Leg 7 of the ATtiny gets connected to leg 12, which is the latch pin of the shift register. Leg 6 of the ATtiny gets connected to leg 14, which is the data pin of the shift register. And finally, leg 5 of the ATtiny gets connected to leg 11, which is the clock pin of the shift register. Now, moving across to the rest of the chaser circuit, we connect 8 rows of the breadboard to the upper ground rail using 8 1 kilo ohm resistors. Into each of these rows, we insert the negative leg of a 3mm LED and insert the positive leg of each LED into a row on the opposite side of the breadboard's gutter. We connect leg 15 of the shift register to the first LED of the chaser sequence using a jumper wire. Then, moving sequentially along the legs of the shift register, We connect leg 1 of the shift register to LED number 2, leg 2 to LED number 3, leg 3 to LED number 4, leg 4 to LED number 5, leg 5 to LED number 6, leg 6 to LED number 7, and finish off by connecting leg 7 of the shift register to LED number 8. We add a momentary button to the breadboard to simulate the red alert input signal and connect one of its legs to the positive row of the breadboard using a jumper wire. We connect the diagonally opposite leg all the way across to leg 2 of the AT Tiny chip. We need to remember to include the 10K pull-down resistor on this leg even if we aren't using the red alert effect. As before, after we add power to the circuit, we can see the chaser sequence running at its own pace. When we press the button to send a red alert signal, the sequence speeds up and the lights move twice as fast until we stop pressing the switch. The number of lights and speed of the chaser sequence can be modified by changing the same settings as the previous circuit before burning the final sketch into the AT Tiny. That's it for part 1. In the next segment, we will be looking at a more traditional and bulky chaser circuit, as well as a second sneaky little circuit which manages to work by using only a decade counter to run the show. Until then, so long and thanks for watching.